binary search trees. We will be discussing the definitions and the operations that are required for binary search trees, and briefly explain the complexity, and then discuss the AVL advantages and disadvantages. In the following sections, we will be talking about AVL trees, spray trees, and multi-way search trees. So, first of all, what's a binary search tree? A binary search tree, of course, is a kind of binary tree, but the difference between a binary search tree and a regular search tree is the following. In the case of a binary search tree, all values that are smaller than the current node should be in the left subtree of the current node, and all values that are greater than the current node should be in the right subtree. For example, if you look at the figure here, all values that are smaller than 20 are in the left subtree of 20, in the yellow subtree. All values greater than 20 are in the right subtree, which is green. This should hold not only for the root, but for all nodes in the tree. So, in other words, for the case of 12, again, all values that are smaller than 12 should be in the left subtree, and all values greater than 12 should be in the right subtree. But we know that in this yellow subtree, we only have values that are smaller than 20. So implicitly, we know that the values in the right subtree of 12 are actually between 12 and 20. Similar is true here on the right side. All values in the left subtree of 26 are between 20 and 26. Here it happens to be a single value, which is 22. And all values that are greater than 26, we know they're already greater than 20, but if they're also greater than 26, then they're on the right subtree. Again, let me emphasize once again that this should hold for all nodes in the tree. Otherwise, it's not called a binary search tree. Now, what type of operations do we need? First of all, we need search. Search is simple. Since the tree is a binary search tree, and what I'm searching for, if it's less than the root, I will look at only the values in the left subtree. I don't need to look at the values in the right subtree. So in this example, if I am searching for a value like, say, 18, when I compare 18 against 20, I know it should be in the yellow subtree. So I get rid of the green subtree, which means I get rid of almost half of the search space. The search space is a set of all values. So I get rid of almost half of the search space, but with a single comparison. So this single comparison has cut the search space into almost 2. Then I compare against 12. Again, if the value is smaller than 12, it should be in the left subtree, otherwise it should be in the right subtree. I was searching for 18. 18 is greater than 12, so I know it should be in the right subtree. Therefore, I get rid of almost half of that remaining search space. So again, I cut by 2. So in every step, in every comparison, I cut the search space almost by 2. So the search space diminishes very quickly. In every stage, you're splitting almost by 2. So this is how search is done. We need to implement the search. Insertion is very similar. Actually, to do insertion, you first need to find where you should insert the value. So you first do a search. When the search completes, if it was an unsuccessful search, you also found where it should have been. Because when you're searching for it and you find that it's not in the tree, actually you have come to the place where it should have been, but there's nothing there. There is typically a null pointer there. So you create a new node and place it there. So that's how you do insertion. Deletion is a little bit more complex. When you delete an element, okay, you delete that node, but if the value you're deleting, if it's a leaf, like if you're, say, deleting 9, no problem. Just delete 9 and make this pointer null. But if you're deleting, for example, 12, then it's a trouble, because when you delete 12, the rest of this yellow tree would be disconnected from the other part of the tree. To avoid that, there are two different approaches. Either you pick the largest element in the left subtree of the deleted node, which was 12, or the smallest in the right subtree, one of these. Okay, so that means you're picking one of the values that was closest to the value that has been deleted. One, the nearest ones are 9 and 14. And whatever that value is, you pick one of them. You put it in the place of 14, sorry, 12, in the place of 12, and fix the tree. So, for example, we would be moving 14 to the place of 12 when 12 is deleted, and 18 therefore would move one level up, and the other three elements would be smaller than 14, so still it's correct. Or an alternative approach would be taking 9 all the way up here, and then 14 and 18 would remain where they are. These are two different approaches, but as we've seen, deletion is a little bit more complex than addition. And another operation that we need is retrieval in a sorted manner. This is especially important in the case of databases. In the databases, sometimes we need to list all of the values in the database, for example, sorted according to a key. So that's when we need it. How about the complexity? Now, the average complexity of the binary search tree is O log n, just because of the reason we explained. What we said was, remember, we are taking the 3 and splitting it into half, let's say from here, so we get rid of, for example, the green part. So then we split once again. In every comparison, you split the search space into almost half. Not exactly, but sometimes what you're discarding will be less than half. Sometimes it will be more than half. On the average, it will be around half. So if you're dividing the search space into 2 in every comparison, your complexity on the average would be O log n. But pay attention, it's the average complexity. If the binary search tree is somehow unbalanced, then the time required to find what you're searching for varies significantly, because, for example, if you consider the figure here, what you're searching for, if it's less than 20, you discard the right part of the tree. That means you're discarding more than half. You're lucky. But if somehow what you're searching for was more than 20, then you would be discarding a very small portion of the search space. So depending on what you're searching for, sometimes it runs fast, sometimes it's quite close. So that would be a difficulty, a problem for us. Well, the problem gets worse if somehow the input is biased. Like if the input is going as, initially you had an empty tree, so you had only the value 1, okay? So we initially had an empty tree. When we have the input 1, sorry, let me just pick up. I somehow couldn't get the pen. Okay, I will not be able to draw. I'm sorry. So initially we have an empty tree. So if the first input is 1, we'll put 1. Then the next input, say, is 2. So 2 is greater than 1, so 2 goes to the right of 1. Then the input comes as 3. So 3 is greater than 1, so you check the right link. You have 2 there, so 3 will go to the right of that. So this way, if the input is ordered, then you have a binary tree. This is still a binary tree, but all left nodes are just nulls, and you will end up with a binary tree which looks like, in fact, a linked list. So what was the complexity of the linked list? On. So the complexity, the worst case complexity of the binary search tree will also be On. Now, how likely is it that this happens? Well, it will happen if the input is biased, like if the input is ordered. Here in this example, the input was entered in the order 1, 2, 3, 4, 5, 6, 7, 8. That's why we had this tree. If it was entered in the reverse order, 8, 7, 6, 5 in that way, then we would have a left skewed, right? This one is called a right skewed tree. If it was in the reverse order, it would be a left skewed tree. But anyways, it would not be a balanced tree. So when we have such skewed search trees, we have the worst case complexity. So what are the advantages of the binary search tree? Well, it's simple. Most important thing is simple, and it's also efficient. As long as the input is not biased, therefore we don't have a skewed binary search tree. If the tree is close to balanced, it works pretty well. So to have a nice performance, a reasonable performance from a simple algorithm, that's exactly what we want. It's dynamic. Dynamic means the following. You might end up with a solution that works better. But if the tree is slightly changed, or if you want to add a new element, you have to reconstruct everything from scratch. Then this is not a good approach. In the case of a binary search tree, if you want to add a new element, you search where it should have been and just create a new node there. So it's also dynamic. And for these reasons, it's one of the most fundamental algorithms in computer science, and it's the method of choice in many applications. The shape of the tree, for the disadvantages, the shape of the tree could be easily degenerated because it depends on the order of the insertions, as we have discussed. And when you're trying to insert or search for an element, the key the key of each visited node should be compared with what you have in hand. So every node you visit, you have to do yet another comparison. And if this comparison is slow, then the whole algorithm will be slow. Why would that comparison be slow? Consider long keys, especially, for example, if the keys are strings. Now, if the keys are integers, no matter if it's a short integer or a long integer or a double, whatever, it doesn't matter. The time of comparison is fixed and not too long. However, when we talk about string comparison, you have to compare the characters one by one. You take character 0 from both strings, compare them. If they're the same, compare character 1, 2, 3, 4, 5. So if the strings are long, and also if the strings have similar prefixes, that means the first few characters of both strings are the same, you have to do many comparisons, and this will significantly slow down your algorithm. So these are the disadvantages of the binary search tree. Can we make performance improvements on binary search tree? Yes, there are two different approaches. One is you reduce the time for the key comparison. So you make use of the radix tree search algorithms. There are several of them. So you compare on the first leading bits, and if you, whenever you see a difference, okay, they're different. So you just stop comparison. This will speed up. Another approach is you keep the tree balanced. Remember, for the case of a balanced tree, it runs with O log n. So as long as the tree is balanced, it has a performance of O log n. Now the question is, how do you keep the tree balanced? And to keep the tree balanced, if you're spending too much effort and the balancing operation itself is too costly, then it's not worth it. But luckily with the AVL trees, we have simple rotation mechanisms which are not costly to keep the tree balanced.